All right, let's talk about some things with graphing polynomials. Graphing functions of the form ax to the n. Let's look at some examples where n is odd. If n is odd, we could have ax cubed, x to the fifth, something like that. I didn't space these very well, so I'm going to just do ax over here on the right one, because I think we all know what a line looks like. It's just a straight line. If we look at doing a cube, the traditional one we know is like this. That looks more like x to the fifth, to be honest. Let's make this x to the fifth. X cubed isn't as flat when it's close to the origin. So we'll do x cubed here. So the difference between these base ones is like this like stays flatter until it gets to 1. Now, these aren't the only forms of x cubes. If I do something like f of x equals x cubed plus x squared minus, oh wait, let's hold on, x cubed minus 2x squared plus x. That's what I want to do. It actually looks like this. At 1, it goes there. It does our normal thing at 0. It does something like this, though. So they don't all make the, sometimes there's up and downs. Maybe I should have did that a little bit better. So just because it's odd doesn't mean it just does this weird thing where it changes direction and that's it. We can do ups and downs like that. In fact, the number of ups and downs we can do are n minus 1. Well, what I mean by ups and downs is it changes direction. So here it changed direction here and it changed direction here. This holds true with any of them. If I do x to the fifth, I can get 4 wiggles or 4 changes. It's true on the even functions as well. So let's take a look at the even functions. Anyone have any questions so far? You might actually like this section because even though we're going to graph some horrid looking shit, you're kind of like you only really need to show a few points. And after that, your accuracy is going to be like, fuck it. I think it looks like this. And so it looks like this. It's going to be like that. Let's take a look at when n is odd or even. Like ax squared, ax to the 4th. We all know our standard ax squared is a parabola. X to the fourth looks similar. It's a little flatter as it goes over to the 1, and it gets a little steeper after that. It's still got a U shape. And x to the 6 is even more like very, very, very flat until we get to the 1s and takes straight off. In fact, this might be worth showing on Desmos. So we got a good old picture of x to the 4 or x squared. When we do x to the 4th, the green one, notice is a little flatter near 0. It's like flatter near 0, but then as it goes past -1 and +1, it starts going up higher quicker. If I slap in x to the 6th, it's even more flatter as it's near 0. And then in both directions, but when we get past 1, it starts getting higher quicker. So like for any value past 1, the x to the 6th line is above the x to the 4th line, which is above the x squared line. But the base graphs look very similar. They're all U's. So that's handy. Of course, x to the 4th can have some wiggles or some changes. We could have several changes in there. I could have something that does that for x to the 4th without slapping it on a graph somewhere. This has 3 changes. It's going down, then it starts going up, then it starts going down, and then it starts going up. Again, n-1 direction changes. Tops. That's the maximum number of direction changes we're going to have. As we can see, they don't always have a direction change. Ax to the 4th with nothing else on it doesn't, it only changes direction once. So what are some properties of this, the ax to the n functions? They look like they're symmetric about the y-axis. Even. Domain and range is infinite. Well, domain is infinite. Range isn't. The base one for ax to the n is 0 to infinity. It's decreasing from -infinity to 0. And it's increasing from 0 to infinity. They are continuous everywhere. Continuous on their domain. We never have to pick up the pen while drawing it. What about the even or the odd functions? Just put a picture up to look at it again. And we're really looking at the one without the wiggles so far. So maybe one of those, x to the fifth or x cubed. Here we say these are symmetric about the origin. And I'm going to have to draw a really big picture and kind of draw it to show you what I mean. Because this is really trips me out. Like it took me a long time to figure that shit out, what it meant. The domain and range are infinite. It's everywhere, all real numbers. It points down on the left. And up on the right. And it's increasing everywhere. It's increasing and continuous everywhere. All right, so how do these graphs get changed? Making edits. This is true for all ax to the n, the following information. So for f of x equals ax to the n, any n, if the absolute value of a is greater than 1, the graph stretches vertically. Positive y values get larger than they normally are. It makes it look narrower. So if I have x squared like that, that might be 2x squared. So it makes it so it looks narrower, but what it's really doing is grabbing every y value and stretching it up higher. If it's less than 1, and we're still talking about the absolute value here, the absolute value is less than 1 or greater than 0. If it's 0, then we don't have a graph here. It shrinks it vertically. Which makes it look wider. So maybe if I had a graph like this, that might be 1/2 x squared. It's kind of, or graph shrinks vertically, kind of makes it look flatter, doesn't it? It's like it's flattened down. If we have negative ax to the end, the graph is reflected across the x-axis. If we have something added to it, yeah, we're bringing our h and k into it, like we had with circles and shit. It goes up k. Or down if k is negative. Then we have the option of a times x minus h to the n. It's shifted right h units, the entire graph, or left if h is less than 0. And these two things are called translations. When the graph looks identical to the base graph, like if we do x squared and then we do x squared plus 2, it's just the x squared graph moved up 2 units. It's called a translation. And obviously we can do combinations of this. Translates both ways. All right, you guys ready for more? So let's do some examples. Enough of the rules and the jibber jabber. What does all this shit mean? Let's take a look at like what x cubed plus 4 is, or minus 4. Let's do minus 4. The base graph of x cubed is like that. If I want to do x cubed minus 4, I am literally just shifting that graph down 4 units. Other than that, it's the same graph, it's just moved. If we have x minus 2 to the 5th power. Let's make it squared. It's really hard to see the difference between the 5th power, the 3rd power, and b squared. So the base graph is, our good old 1, 1, 2, 4. We've done parabolas. Base. That is sloppy. It should look a little more rounded. Mine looks like a point. This is x minus h. So h here is 2. Which means we're going to move the graph right 2 units. And do the same thing. 1, 1, 2, 4. So it just shifts or moves the graph up and down. It moves it all around. Ready for more? We can make it a little bit harder. So my HK here is what? -3, 5. So it looks like I'm gonna have some action going on up here in this second quadrant. It's an x to the fourth power and is even. So a regular n equals 4 is like that. The negative is going to flip it over. So negative x to the fourth is like that. And the 1/2 kind of flattens it. So if I go right 2, I would normally go down, oh shit. If I go right 2, I would go down 6 or up 16. 2 to the fourth power 16. I would go down 16, but since it's cut in negative half, 2 for x to the fourth will be right 2 up 16, but now we've got a negative 1/2 there. So when I go right 2, I go down 8. And the negative 1/2, when I go left or right 1, I would go down 1. Now I'm only going down 1/2. When I go down left or right 1. So it's kind of going like that. I don't know exactly where it crosses. Here we're sketching the graph. We're not going for 100% accuracy. If we want accuracy, we're not going to have you do it by hand. You're going to do it on a computer, right? But when you're done doing the homework for this section and the next section, when you see an equation and you're comfortable with how it works, when you see something graphed, you'll know information about it just by looking at it. So unless otherwise restricted, the domain for all of it is all real numbers. For any of them. Whether n is odd or even. They are said to be smooth and continuous curves. So this is polynomials in general. Which means we don't have any jagged things like absolute value. There's no cusp like on absolute value. It might go pretty steep, but you're never just rapidly like ricocheting off something. The next bit of information, I'm gonna draw 3 graphs for you, and we're gonna like see how it works from there. So we have f of x equals x. say x minus 2. Here I will do x squared. Here, let's put x cubed. Nope, that's not x cubed. That's x cubed. I got a little distracted. My root for this one, when I set it equal to 0, it's crossing at 2. So x equals 2 is a root. My roots for x squared, if I set x squared equal to 0, I have two solutions. This is like x minus 0 times x minus 0. I have 0 as my root with multiplicity of 2. So multiplicity is how many times the answer should is how many times a value shows up as a root. For example, x minus 2 squared, x plus 3 cubed. X equals 2 has multiplicity of 2. X equals -3 has multiplicity of -3. Or 3, not -3. So it's really how many times does that parenthesis show up as a factor? If I go back up and look at the x cubed, I could say x cubed, just the base graph of x cubed, has root 0, multiplicity of 3. Because I could really write it as x minus 0 cubed. If I want to make it look like this factor kind of thing. All right, so let's take a look at what this, why I even bothered saying this. Oh, I'm sorry, you're still writing. All right, so my f of x line, x equals -2, this had multiplicity of 1. When you root, these we're all talking about roots. And this is my x-axis. If we have multiplicity of 1, it crosses the x-axis as a straight line. If I have multiplicity of an even number, we don't cross the x-axis there. It actually bounces off. So it might bounce off at the x-axis. Or it might come from below and bounce off going that way. So it bounces off or ricochets. And if we have multiplicity of odd greater than 1, we see the bouncing thing from the y equals x squared graph. Actually, see that? It hits the x-axis and it bounces off. What is the cubic doing? It hits it, it goes across it, but it doesn't go across it like a straight line, right? It kind of like wiggles across. And that's true of any multiplicity of odd. It's kind of like wiggle across. So it's not a straight line. I call it the wiggle. Do they have a term they like to use? Nope, they use wiggle. In fact, it even uses wiggle. It wiggles over the axis. All right, some more information. Oh, I can put it on here. Remember when I was talking about how it changes direction n minus 1 times? These are called turning points. I can give you a name for it earlier. Those are called turning points. And that's at most n minus 1 times. Like x cubed could have 2 turning points, but it doesn't. The base graph of x cubed just keeps going up. It wiggles, but it just keeps going up. I think we're gonna do 3.4 today, finish 3.4 today, and 3.5 tomorrow, or Thursday. And wait for 4.1 after spring break. Because these are the graphing sections, and these are the ones that like, there's a lot of work to graphing once you start doing them. Want to make sure you guys get what's going on. So, what's some more information before I start making life living hell for you? End behavior. It's called end behavior. And let's see, to trigger this or motivate this talk, I'm going to grab a page we had at the beginning. A couple pages we have. Let's look at n equals odd. If A is greater than 0, and A is the coefficient on x to the n. Like I could have ax to the n, bx to the n minus 1, cx to the n minus 2, dot, dot, dot. If A is greater than 0 and n is odd, I have these type of circumstances right here. As x goes to positive infinity, f of x or y goes to positive infinity. And as x goes to negative infinity, f of x, which is still y, it goes to negative infinity. So if we're talking about the end behavior, this is just like what happens ways away from the origin. What happens at the end? This one's going up on the right and it's going down on the left. And it doesn't matter if I've got x, x cubed, x to the 5th, x to the 7th, x to the 9th, x to the 1,000,001. If it's an odd exponent and the number in front of x, that leading term is positive, it's going to do this when it goes to the ends. If A is less than 0, it kind of switches this around. As x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to positive infinity. So it's doing this. It can do a whole bunch of shit in the middle. But when it's at its final direction change, that's what's going on. What can we tell looking at the even graphs? They both go the same direction, right? So for n equals even, and the ones I've got pictured, A is positive. A is greater than 0. They go the same direction. Well, they go the same direction with whether A is greater than 0 or A is less than 0. As x goes to plus or minus infinity, f of x goes to positive infinity. It's like it, put your hands in the air. And if A is less than 0, this switches. As x goes to positive or negative infinity, f of x goes to negative infinity. They both go down. That was why I do all those graphs in the beginning. You can kind of see when you look at a bunch of them, they're all doing similar shit. And I put up 4 different functions, and your job is to tell me what the end behavior is when we do it. So am I on screen? Okay. That's what's happening on the left. It's going down. What's happening on the right? It's also going down. We're looking at that exponent right there. That exponent is even. So they go the same direction. They're either going up or going down. And the negative says make it go down. What about x cubed? G of x.
The left side is going up. The right side.
Like that? You guys agree?
Oh, so
It is the other way. This one you had it right. That one's doing that.
that's what I was doing.
And this one's throwing its hands in the air. Actually, we will get started on 3.5 today. Other than doing examples, we're almost done. So, how do you graph a polynomial? So, step one, step A. Find the zeros or roots. Those give you actual points on the graph that are easy to find. Well, relatively easy to find. Should also find the y-intercept. After that, you will use end behavior to figure out what's going on the ends. And then you're going to check to see crossing, bouncing, wiggling over the x-axis. At the roots. And then just connect the dots. Making it look curvy. Find the y-intercept is actually the easiest one. Because the y-intercept is when x equals 0. So you're plugging in 0, and it's the remainder. It's the single term that doesn't have an x in it. All the x's go to 0, so it clears out all the coefficients there. Just whatever's left. That's your remainder. The book and stuff will call this a sub 0. So it will look like if you're looking through the book and stuff like that, or in the stuff online, they'll say a n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 1 x to the first power plus a sub 0. That's the general form. I still think I'm gonna not do 4.1 this season. Yeah.
What does the like the end being below A, what does that what that do?
It's a subscript. It's just to identify which term it's on.
Oh, because I didn't know if it was like a.
No, this is a subscript to identify. Good question. Which term it is a coefficient for. Like you will never see a subscript when there's an actual number there. You're not going to have a 3 with a subscript of 1. It's only on these things with like coefficients or stuff like that. You guys ready? The hell? Oh, what's this? Do that in a second. Let's just go fucking crazy. I'll give you f of x factored for this one. So what are my roots here?
Two.
Anything else? You said -3, right? The x in front gives us 0 as a root. So my x equals 2 has a multiplicity of 1. My x equals -3 has a multiplicity of 2. X equals 5 is multiplicity of 3. And x equals 0 is multiplicity of 1. Oh, I made this ugly. How can I fix this? Fuck it, I can't. What about the y-intercept when f is 0? Oh yeah, this one's fine. What happens when x equals 0? It's 0. Right? You plug in 0, but the x out front just kills the whole thing. You don't even need to deal with the rest. I was trying to deal with the rest, plugging in 0 and going, that's -125. Oh, this is good. I can't graph that. If I can grab an x out front. All right, so. And I'm gonna make it a little bit smaller. That way I can fit the x equals 5 on there reasonably. And this is my x equals 5 right there. And this is -5. Okay. So my roots are at 0, at +5, at -3, and at 2. Loud as fuck. I started having fun in college. All right, so what's going on in each one? What's my end behavior? This is where I got to start with my end behavior. What is, how many, like, if I multiply this out, what is my end here? Well, I've got a 1 on this one. I've got a 1 on this one. 1 + 1 + 2 + 3 is 7. If I multiply all the x's together, I'm going to have x to the 7th power. So, and a, the number in front, is 1. Which means I've got an odd number. I'm going to put my right hand up, left hand down. which means I don't know where it's gonna end up, but it's somewhere over here, and I'm gonna have something going on over here. Five has a multiplicity of 3, which means it wiggles across. So I know it's going to infinity that way, it's gonna kind of wiggle across. When x equals -3, it's got a multiplicity of 2. I know it's coming from the negative side, it's gonna come up and it's gonna bounce off right there. All right, so we cleared the 5 and the -3 so far. At 0, I know it crosses 0. That's my y-intercept also. And that means it's gotta, I don't know where it changes, but it's gotta turn around and change. And it's got a multiplicity of 1, so it crosses kind of like a straight line in that spot. And I don't know how high up it goes, but I know it has to cross again at 2, which means it's going to be going down. And I'll just connect the lines up here. That's kind of how you do it. Notice I don't have a lot of precision going on. I didn't bother to find this shit. Like where's those points at? How high up does this thing go up before it starts coming back down? I didn't do any of that shit. You will do it in calculus. In calculus, you will find those turning points, where they're at, and then stuff like that. Here, we're just learning the basics of it.
That sucked.
What?
That sucked. Mine was.
No, it's relatively easy. It's actually one of the easiest things you do in calculus.
Actually, maybe not.
In fact, you guys have done part of it already in your exam. It was the derivative. It was the f of x plus h minus f of x over h. Well, those of you that did that. Some of you didn't do that. I will get back the test on what is Thursday or Thursday class, right? So that can be good. Let me make up one for you guys to do. And I'll give you a couple minutes to do it, and then we'll do it together. What we did on this wasn't really any overly challenging math, was it? It's just, there's a lot of shit to remember. That's all it is. It's not difficult math, it's just a lot of memory shit. Yeah,
So the numbers that you added up, like the end of the song.
yes. And if there's no exponent, put a 1. That's a shortcut way of noticing what goes on. If you multiply it all out, you will get on this one, like the last one, an x to the 7. And I didn't need to multiply the whole thing out. I just effectively, I like zero out all the things and just multiply all the x's together.
Why do you have to tell me there's easier ways to do things when I'm doing it the hard way?
It's the same way I did it in the last example. I added up the exponents. Did you actually multiply it all out?
No, like for example, the y-intercept. I forgot you can just put 0 in and just for the x and solve it. I'm multiplying it all out.
Oh shit, the 0 here is gonna be crappy. Oh, that's gonna be really crappy. Oh shit, everybody's probably already halfway through it. Oh, fuck it. This is gonna be 4 to the 5th power for the 0. Which is what's fucking 1024. Did I just do that in my head? Look at that, bam. Like a boss. So we're gonna kind of simulate that when we get to, I'm not gonna like draw that. I strongly recommend you don't make that to scale with the y-axis. Right? This was not a good example, like, yeah. All right, so what are my roots? Oh, it didn't help that I made them the same values and just changed the signs, did I? That's not much of a challenge. What's the multiplicity on 2? Or negative, change this. Just say it for me, David, say it. Multiplicity on 1. 1. Multiplicity on 4. Multiplicity on -1. So this is kind of going to do a bounce. This one's going to cross. This one's going to cross, and this one's going to do a wiggle. I don't know if it's going to go up or down, but I'm just noting what happens when we get to the x-axis there. F of 0 is 1024, right? So I'm not giving myself a lot of room. Let's put it down here. That's my x-axis. That's my y-axis. This is my trash line. I've been fucked up. Let's put some roots on there. I guess I do need to label. That's my y equals 1024 line. There we go. That's what that line is. So I got a root there, I got a root there, I got a root there, and I got a root there. What does my end behavior look like? What's going on the left? What's going on the right?
Oh, left, it's going down.
I was gonna let you say it. On the right, it's going up,
I was
right?
looking at the coordinate where your pin was.
Oh, yeah, I'm like, yeah. Okay, so that tells me we're down here somewhere and we're over here somewhere. Let's work inward. Oh, and we know that the y-intercept is there. -4 has a multiplicity of 2. What does that mean is going to happen when I get to x equals -4? It's going to bounce. It's going to bounce upward and it's going to have to come back down. What about +4?
It's gonna do it.
It's going to do the wiggle, right? All right, I can see kind of what has to happen. This has got to go up and cross and come up here. The question is, how does it cross? It crosses as a straight line. It doesn't wiggle across. I don't know what the left or right is, so I'm just doing it that way. You guys ready to do a hard one? It wasn't hard, was it?
It's 0. It's
The 0 is actually not hard. You got 4 squared times -1 times -4 cubed times 1. That's calculator. Not even, I did it in my head. How hard can it be? All right. Now I can tell right away my end behavior. A is positive and it's an x cubed. I'm going to have something going on like that. And I can also see right away where my intercept is. This one is the right setup to do it. F of 0 is -6. The rest is where we kicked it up a notch. How do I find the other zeros? This was all that P over Q shit. So Q is ±1, ±2. P is ±1, ±2, ±3, and ±6. So we can have all the P's over the Q's, Q1 equaling 1. And so ±1, ±2, ±3, ±6 are valid. Then I could put them all over 2. And I could get a ±1/2. I could get a ±2 over 2, but 2 over 2 is 1. I already got that. I could do 3 over 2 and I get 3/2. I don't have that yet. And I could do 6 over 2, which gives me 3, and I already have that. So if I write these out, Those are my options. Now, for those that were here for the math 335, and it's worth checking out later on, because we just, all we did was like a bunch of problems with this, figuring out, finding roots and shit. I like to start with a whole number somewhat near the end, see if I can get rid of shit. Let's start with, I don't want to use a fraction. Let's start with 2. So I'm going to try to do 2 into this. Bring the number down and we'll multiply it and add it up here. That worked. This gives us, since it's a 0, this gives us x minus 2 as a factor. And what we have left is a polynomial of 1 degree smaller. So my f of x right now is currently that. At that point, I can factor. Let's see, I need to multiply to 6 and add to 7, which is going to be 1 and 6. So 2x squared plus 6x plus x plus 3. And I ultimately get x minus 2, x plus 3, 2x plus 1.
I have a question.
Yeah,
So if the leading coefficient is not 1, doesn't that mean that one of the roots has to be a factor?
wait, what?
Right? Because 2x plus
Say
1
say
is
what you said again. You said one of the roots has to be a factor. Did you
not a
mean
factor. One of the
fraction?
roots, fraction, yes. Wrong word. Because 2x
Not
plus 1,
necessarily.
not necessarily.
We could have a 2 out front. It didn't happen in this case, but it is possible.
Okay.
We'll look at an example in a second with it. I'll make one up. So what are my roots here? Not -1. -1/2. So if you need to set each one equal to 0. They are all multiplicity of 1. I know my end behavior is like that. And I know f of 0 equals 6, -6. And if it's down here, it's going up over there. And I know everywhere it crosses the x-axis is kind of like a straight line. So I'm just gonna do that. Probably does a little bit more like that. Not that bend I did. That's it. That's all there is to it. So let me give you guys one. Let's see. Even though I haven't handed out the test yet, you all can see your grades on cameras. If you did not do as well as you like, and you're not in class from 2 to 3, come on in at 2 o'clock. We're doing problems from like what we're doing today. I'm gonna do an hour of this kind of shit from 2 to 3 on Thursday. So like if you didn't do as well as you want, you can come in and start getting extra like practice in. So you can make sure you're doing, but you do the best you can, assuming you don't have class or work at 2 o'clock. And you need help or something. If you did great, you got an A, you say, fuck it, I don't even come. I hope you guys didn't try to do this the hard way. Did you guys try to do this the hard way? Did you try to treat this as a cubic? And do P over Q and shit like that? I deliberately designed this problem to skip the P over Q thing. We can factor out not just a 2, but an X, can't we? And when you factor that, you get that. So that answers your question, whether or not a 2 and 4, something besides a 1 in front forces us to have a fraction as a root. What are my roots like?
Two.
I'm gonna get you on the test on this one, Bennett. 0. So set each thing equal to 0.
I always forget it.
It's easy to forget. It doesn't have parentheses. It's just sitting there innocuous. It's like a ninja just fucking hiding. Right in plain sight. It's right in front, hiding in plain sight, right in front, and it's like. I guarantee. At least one student will miss that on the test when we have it. Hopefully not. If you do, start recognizing now, you prevent it in the future. Tends to be a lot more than 1 though. All right, what's the multiplicity on these? They're all 1, so they all kind of like cross the straight lines, right? I don't know in which order. What's my end behavior here?
Side down.
And what's my y-intercept?
0.
0. I'm crossing at -2. I'm crossing at 1. And I'm crossing at 0. And that is my y-intercept. I know it's coming from down here to the left and up here to the right. And I know it's crossing as a straight line at every point. So it's going to cross. Generally, where it changes direction is about halfway through. That's usually what I approximate it by. So I made it change direction at -1. Here I'll make it change direction at +1/2. That's usually a good spot to do it. Rarely does it change place like somewhere not halfway through. That's it. That's all we got. That is 3.4. We will do 3.5 on Thursday. We will have variables in the denominator. Yeah. We're gonna graph that shit. Yeah. Woo. You're gonna get asymptotes, you're gonna get vertical asymptotes, you'll have horizontal asymptotes, you'll have something called the oblique asymptote. It's a diagonal asymptote. Does it? Yes.
If you don't mind, can you go over how you get P's and Q's again, by the way?
Yeah. So, P's and Q's. In general, without specific example, if I have a sub n x to the n plus a bunch of shit plus a sub 0 at the end, P are factors of 0, a sub 0, which is the constant. Q are factors of a sub n, which is the leading coefficient. So if I have something to make it simple. Well, not simple. So the reason why we do the plus and minus of everything is, like for the -30, I could do +1 and -30, or I could do -1 and +30, and they both multiply to that, which means they're both factors of that. So I tend to do them like that. If it helps do them in that order to begin with, so like just start with the first and the last number, then try, does 2 go into it? 2 does go into it, 2 goes into 30 15 times. 3 goes into it 10 times. 4 doesn't. 5 goes into it 6 times. And as soon as I start going up past 5, I get to 6, now I'm doing the other numbers. So those are all of the factors of P. Now, I think it's a little bit easier to have them when you're doing the next step, to have these in increasing order. So I'm going to do that real quick. These are my P's. And they can all be plus or minus. My Q's are factors of 6. Factors of 6 are 1 and 6 and 2 and 3. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So one way of doing this, if it helps you, right, make it like a list of the Q's. You don't need to bother with the sign for now. Oh shit, this is actually a great way to do it. I'm coming up with a new way to explain shit right now. And we're doing the row divided by the column. So dividing by 1 is easy. I'm gonna get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. If I do, now I'm going to do P over Q on the 2 row. 1 over 2 is 1/2. Two over 2 is 1. 3 over 2 is 3/2. Five over 2 is 5/2. 6 over 2 is 3. 10 over 2 is 5. 15 over 2 is 15 over 2. And 30 over 2 is 15. Generally, I'm doing this as I go left to right, and I don't make this table. But notice what happens. Some of these numbers are already on the list. Plus or minus 1 is already right there. I don't need it. This is a duplicate. In fact, anything that doesn't have a 2 in the denominator right now is a duplicate. So I don't need it. Now we do the 3s. Doing 1 over 3 is 1/3. 2 over 3 is 2/3. With of course, with the plus or minus 1s. 3 over 3 is 1. 5 over 3. God, I can't, this one has a big list, doesn't it? 2. So I'm just dividing by 3 on each of them. My 1, my 2, my 5, and my 10 show up on the top list. Top row. Maybe I'll throw in the plus or minuses now. If I do it here, divide by the bottom row, divide by 6. And then I'm going to look to see if any of these show up somewhere else. Two over 6 reduces to 1/3, right? So 2 over 6, I don't need it because it's already on my list. 3 over 6 is 1/2, which is also on my list. I don't need that one. 6 over 6 is 1. Don't need that one. 10 over 6, if I divide top and bottom by 2, I get 5/3. That's right there. I don't need that one either. 15 over 6 is actually 5/2. If I divide top and bottom by 3, I get 5/2, and I have 5/2, so I don't need that one. And 30 over 6 is 5, and we already seen we crossed that off more than once. So this one would have a lot of fucking things to check. This is where you start being strategic about it. And like not doing the one right away at the ends. See if you can get numbers that cancel out, like with the theorems that we had. Ideally, when you do more ideas for helping in this section, if you find out, like if you do like f of x has got like an a sub n x to the 5th power plus a bunch of other shit, and you do the rule of signs, the Descartes things, and you show that you have 4 positive roots and 1 negative root. Focus all of your testing on the section that has more answers. Try only positives. Because there's 4 of them. I have a much better chance if I pick a random positive number from my list of it being one of the numbers I need. Whereas if I pick a negative number, how many fucking negative numbers did I have on this one? How many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 16 positive numbers and 16 negative numbers. If I aim for a negative number, I got a 1 in 16 chance of picking correctly. If I aim for a positive number, I've got a 4 in 16 chance, or 1/4. I got better odds of getting the right number if I start with a positive. Which means you can start narrowing that list down quicker. And as soon as you get down to a square, as soon as there are only 3 things left, 3 numbers left from synthetic division. You have an ax squared plus bx plus c. And you can factor, you can do a quadratic formula, you can do other shit at that point. Don't keep going with the p over q. So there are ways to be more productive in your approaches. That's a horrid problem I put up there. That's ugly. Does that help?
Yeah.
A lot of people don't think about this. Well, you're like, if you've got more, a lot of positive numbers, then you're just like throwing darts. And you got more things that hit are positive than negative, aim for the positive side. All right, GTFO. See you guys on some other day, Thursday.